All right, welcome back. Let's talk about Chapter 4, Section 3. And specifically, we're going to talk about some different measures of variation. We're trying to determine a variety of ways to describe our data. And one way we can do that is by measuring how much the data varies. Let's talk about that next. What we're going to talk about specifically, a few different measures. We'll talk about the range. We'll talk about what's known as the 5-number summary, and then also the standard deviation. The standard deviation is really a default measure of variation. You'll see that it goes hand in hand with a sample mean. We'll get to that soon. So let's kind of introduce these measures of variation by looking at some examples of why we really need measures of variation. So check out this example. Customers at Bank A can enter any one of 3 different lines leading to 3 different tellers. Bank B also has 3 tellers, but all customers wait in a single line and are called to the next available teller. And you've probably been in both these situations where you either queue up right behind a teller or you're just in this one line and then you get to go to the next available teller. Now, of course, companies put a lot of thought into how they want to set this up because they don't want their customers waiting. Well, here's a sample of wait times from both banks. So Bank A, remember the people, they essentially pick a teller and they go wait in line. And here I've sorted the wait times, this is in minutes, from the lowest wait time to the highest wait time. And I've done the same thing for Bank B. That's where there's one line and they just go to the next teller who's available. Okay, so let's first just compute some basic measures of central tendency. So for example, let's compute sample means. So you might recall that X bar represents a sample mean. So if we were to take all of this data for this first group from Bank A, if we summed up all those wait times, the value would equal 79.2. There are 11 wait times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we divide by 11 and we'd find that the average wait time is 7.2 minutes. All right, let's compute the average wait time for Bank B. And again, I'm just going to add up all these values and divide by the number of values. Again, there are 11. Well, check this out. When I add those up, the wait times again equals 79.2 minutes divided by 11. So the average wait time would be 7.2 minutes. So the means are the same. But when I'm looking at this data, I think the data is telling a different story. Let's compute a median real quickly, another measure of central tendency, to see if that might help us better understand what's going on. So you might recall we have a formula for computing the location of the median. So we know that we have 11 pieces of data here for each particular bank. So I take the n, which is 11, and I add 1, that equals 12. We divide by 2, and that shows us that the median is in the 6th position. So of course we have to order our data from the lowest value to the highest value in order to find the 6th position. So for Bank A, let's find that median. Here's the first position, 2nd, 3rd, 4th, 5th, there's the 6th right here. So that would be the median. Let's find the median for Bank B, 1st, 2nd, 3rd, 4th, 5th, 6th. Check our work by looking from the other end, 1st, 2nd, 3rd, 4th, 5th, 6th. So again, we're finding the same story here. Like there are no differences between these two banks in terms of the methods that they're using to bring their customers to their employees. But again, when I look at that data, it looks to me like it tells a different story. And that's why what we're learning here is that central tendency can't tell the whole story on its own. Here with these two different sets of data, we have the same medians, we have the same means, and clearly there's something else going on. If you look closely, you'd probably agree that it's likely that more customers from Bank A will complain. I mean, look at this. These people are waiting 11 minutes. These people are waiting 9 minutes. These people are waiting over 8 minutes. That's a long time to be waiting at the bank. So what I'm seeing here is that there's really more variation in these times at Bank A when they have the 3 different lines, and there's less variation in the wait times at Bank B. Here I can see that someone waited for as little as 6.5 minutes approximately, and as much as 7.8 minutes, about 8 minutes. There's less variability we can see here in the numbers compared to at bank A. Well, that's the bottom line. We need some measure to also tell us how much variation there is, because measures of central tendency clearly aren't telling the complete story. All right, that's what we're going to focus on. Let's first talk about a very simple measure of variation, and that's the range. And all a range does is compute the distance between the highest and the lowest values. So to compute the range, we're simply going to take the maximum value, the highest value, and subtract the minimum value. That will tell us the distance between those values. It's really very straightforward. So let's compute the range for the data from bank A. So the range, I'll just use an R, is simply going to equal, in this case, that maximum value, 11, subtracting the minimum value, in this case 4.1 minutes. And in this case, that's going to equal 6.9 minutes. Okay, so that's the range of values there. The range from the lowest wait time to the highest wait time is a range of 6.9 minutes. Let's go ahead and compute the range for the second bank. In this case, the range is going to equal the maximum value, 7.8 minutes. We're going to subtract the minimum value, 6.6 minutes. That looks like that equals a range of 1.2 minutes. So we can see in this case, the range in the data is much lower for bank B than it is for bank A. These customers are waiting very similar amounts of time. These customers are waiting very different amounts of time. So let me ask you a couple questions, because we need to kind of evaluate how much we like the range. The range is very easy to compute, of course, but it's possible that it could have some problems that will leave us looking for another measure. How many values are used to compute the range? Well, in reality, aren't we just looking at two measures? We're just looking at the highest value and we're looking at the lowest value. So there are really only two values are used to compute the range. Now, that leads us to the next question and potential problem. What can make the range very misleading? If we're only looking at two values and we're looking at the most extreme values, the lowest value and the highest value, then the range can be very influenced by outliers. And I'm sure you are thinking the same thing. So if there are outliers in our data, our range is going to be incredibly influenced by it. And then our measurement of the range, in this case, our measurement of variation, is going to be somewhat unrepresentative of the amount of variability in our data. Let me give you an example. Let's say we're looking at quiz scores for Class A and Class B. Virtually everybody has the same quiz scores. It looks like everybody nailed it in Class A, except for this one student. This one student just didn't get it. Look at the quiz scores for Class B. There's quite a bit of variability in here. But now check this out. Which data set has a larger range? The range for Class A would be from 10 to 9 would be the calculation. 10 minus 1 would equal a range of 9 points. The range for Class B would be from 10 down to 2. So we take the maximum of 10, subtract the minimum of 2, and we'd find a range of 8. So in this case, which data set has the larger range? Class A. But again, look, they have almost all the same scores. The range isn't doing a good job of showing that in reality, it seems like there's quite a bit more variability in Class B than there is in Class A. So when I'm asked which data set has more variation, overall, clearly it's Class B, but the range isn't telling that story. So not only is the range very influenced by outliers, like we're seeing right here, it's just probably a little bit too simplistic. Now, it's very straightforward. People understand it. Those are good points. But it's probably a little bit too simplistic. So let's move on to another way of describing the variability in our data that might be a little bit more sophisticated. And specifically what we're going to talk about is what's known as the 5-number summary. And 5NS will, in this case, be the symbol that we'll use to represent that. And what the 5-number summary is using are quartiles to essentially summarize the variation in our data. Let's talk about quartiles. First, let me just list all the quartiles that we're going to be looking at. We'll be looking at the 0 quartile, the 1st, 2nd, 3rd, and 4th. Let's make sure that we can make sense of what all those things are. Let me first draw a little picture. Let's say we have a distribution, and in this case it would be symmetrical, and it would also be a normal distribution. If I were to split that right in two, now I have 2 halves, right? Well, I can take each half and split them in 2. I now have, even though it's not a pretty picture, I now have essentially everything represented right here. Let's start kind of easy. Right here in the middle, we're used to finding this place already. This is our median, right? Where a median is also known as our 2nd quartile. So I'm going to put a little Q2. So the median is our 2nd quartile, and it's our 50th percentile equals the median. So there are really many ways that we can describe that one point. It's the 2nd quartile, it's the 50th percentile, and it's the median. Well, we're familiar with the term median. The median is the point at which it splits up our distribution, so half the scores are at that point or above it in value, 50% of the scores are at that point or below it in value. Well, that's also what the 50th percentile is. 50% of the scores at that point or above it, 50% at that point or below. And we also call that the 2nd quartile. All right, well, our 1st quartile, you might see here, Q1, is going to be the point at which 25% of the scores are at that point or below, and then 75% are at that point or above. Well, we also call that the 25th percentile. It's the 25th percentile. And again, because it's the point at which 25% of the scores are at that point or below it. The 3rd quartile, right over here, is our 75th percentile. So as you can expect by now, it's the point at which we find a score, and that 75% of the scores are at that point or below it in value, and then we'd have about 25% that are at that point or above it in value. The 0 quartile is actually just the minimum value, Q0. So that's going to be the lowest value. And the 4th quartile is the highest value. Highest value. So this would be Q4. All right, so do you see, if we can find all those values in this distribution of scores, whatever we're working with, let's say we're looking at exam scores, if we can find what value is the 2nd quartile, and the 3rd quartile, and the 4th quartile, and the 1st quartile, and the 0 quartile, then we'd have 5 numbers that give us quite a bit of information about the variability in our data. Let's go through an example and you'll see what I mean. So let's look at those wait times for Bank A. So I want to find all of those different values in here for the 5-number summary. And we can do the same thing for Bank B. Well, first thing that I'd like to do is find that midpoint. Because if we can find that midpoint, that median, the 2nd quartile, then it's really easy to find the rest of the data. So let's remember how we do that. The way we do that is by using that one little formula to find the median's location. You might remember it's n plus 1 divided by 2. And that's how we find the median's location. Well, if we can find the midpoint, the median's location will tell us where that midpoint is. Then once we split that distribution in half, we can just kind of use the exact same technique to split this remainder of the distribution in half and this part of the distribution in half. You'll see what I mean right now. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pieces of data right here. 11 wait times. 11 plus 1 equals 12, and 12 divided by 2 equals 6. So we know that our 2nd quartile is in the 6th position. There's the 1st, the 2nd, the 3rd, the 4th, the 5th. Here's the 6th right here. So that right there is our 2nd quartile, Q2. So I've essentially just found the midpoint right here. Now let's just look at the remainder of the distribution on the lower end and the remainder of the distribution on the higher end, kind of separately, because that way we can more easily find their midpoints. So here's 1, 2, 3, 4, 5 different scores. 5 plus 1 would equal 6. 6 divided by 2 would equal 3. So we can find the midpoint right in here. Here's the first, second, third location. That's going to be our first quartile. You see how it was the midpoint based on what's left here. Just like over here, what's left in the distribution, we want to find that midpoint. That's the first quartile. We'll do the exact same thing in here. 1, 2, 3, 4, 5. And of course, that should match what we found here. 1, 2, 3, 4, 5. And we found that that midpoint is in the third location because 5 plus 1 equals 6, and 6 divided by 2 equals 3. So here's the first location, second, here's the third. So this right here would be our third quartile. And we can check our work. First location, second, there's the third. Now remember, the 0 quartile and the fourth quartile just represent the lowest and the highest values. So right here, we've got that 0 quartile, and right here, we have that fourth quartile. So here we've got 1, 2, 3, 4, 5 numbers. That's the 5-number summary. So the 5-number summary gives us our median, our first quartile, our third quartile, our minimum value, and our maximum value. It's quite a bit of information. Let's go through another example really quickly right here. And again, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 pieces of data. So let's find that midpoint. 11 plus 1 equals 12. 12 divided by 2 equals 6. Here's the first position, second, third, fourth, fifth, sixth. So right there is the midpoint. That's our second quartile. We have 1, 2, 3, 4, 5 numbers remaining. We should have 5 over here. 1, 2, 3, 4, 5 remaining. 5 plus 1 equals 6. 6 divided by 2 equals 3. 1, 2, 3. This value represents our first quartile. 1, 2, 3. This value represents our third quartile. Here is our fourth quartile, which is the largest value, and here's our 0 quartile, which is our lowest value. I'm sorry, that's a 0. So there we have 5 numbers that we use to describe how much variability there is in our data. Now, the 5-number summary is very closely related to a graphical component of describing variation known as a box plot. And box plots are created by using the values for the 5-number summary. So they essentially just allow us to see the variation graphically. So let's talk about how we would do that. Let me first show you an example. Let's look at those wait times. This is for Bank B. We see the median right here at 7.2 minutes. Well, in this box plot, the median is represented right in the middle of this box, 7.2 minutes. Now, the way that we show the first and the third quartile is by marking them off and then kind of creating a box around them. So 6.7 minutes, we've got our first quartile right here. 7.7 minutes, we have our third quartile right there. So you see the box right there represents essentially the middle 50% of that distribution between the first and the third quartiles. Then we show the whiskers. These are often referred to as box and whisker plots. We show these whiskers with just a line extending out to the minimum value and a line extending out to the maximum value. There are a variety of different ways to make these box plots, particularly when we have outliers in our data, but this is a very straightforward way to do it. So we have our median right in the middle. We form our box with the first and the third quartiles, and then the whiskers of our box plot go all the way out to the maximum value and our minimum value. Let's go ahead and create a box plot using the data from Bank A. It's not quite as compact. In other words, there's more variability in this data, and it gives us a little bit more room to write. So this is the way I usually go about it. I start with that median value, 7.2. So that's going to be somewhere right around here. Then I find my first quartile, 5.6. That's maybe somewhere right here. I find my third quartile, 8.5. That's right around here. And now I can, if I'd like to, draw my box. All right, and at this point I need to draw lines out to the maximum value. 11 is right here. I'm going to connect it. And the minimum value, 4.1, is right about there. I'm going to connect it. So now can't you see, just at a glance, there's clearly more variability down here than there is in this plot right over here. Clearly more variability. Okay, and we're using those 5 numbers to create that box plot. All right, let's talk about another way that we can quantify variability. The 5-number summary allowed us to quantify things really well. It allowed us to create a box plot in which we can visually see things. But there's going to be one more measure that we're going to talk about today, and that's the standard deviation. The standard deviation, which is simply denoted with an S, that's a standard deviation for a sample of data. We would just use an S to symbolize that, is really going to be our default measurement of variability. Just like the mean is our default measurement of central tendency, the standard deviation is typically the measure that we use, all things being equal. And you're going to see the standard deviation that we compute right now and the mean go hand in hand. And that's because the standard deviation will calculate how much the scores deviate from the sample mean on average. So as you're studying, you want that phrase to go through your head over and over and over again as we compute this. What am I computing? I'm computing on average how much the scores deviate or differ from the mean. So that mean is serving as a baseline. Remember I said the mean was the only measure of central tendency that had a mathematical formula. It was the only one that was derived from a mathematical formula. And being that that was the case, it would then serve as the basis for more advanced statistical procedures. Well, here you go. The standard deviation is a more advanced statistical procedure, and it's based on that mean. So that's why they're typically reported together. You'll see in a research report, and in the research reports that you'll be working on, when you report a mean, you almost always report the standard deviation right along with it. Let's talk about the formulas that we'll be using. The sample standard deviation will equal the square root of the sum of the squared deviation scores. So right up here in the numerator here, we're computing what is known as the sum of the squared deviation scores. And we're literally summing up squared deviation scores. What does that look like? In summation notation, it looks like this. And we've done this in class. We've computed the sum of squared deviation scores. Why do I keep calling them deviation scores? We're just looking to see how much each score deviates or differs from the mean. And then we simply divide by the total number of values, otherwise it's known as n minus 1. Once we find this fraction right here, we take the square root and we have our sample standard deviation. So we're going to focus on the sample standard deviation simply because it's much less likely that you're ever going to encounter population data. And the formula for a population standard deviation is almost exactly the same. You simply divide by n instead of n minus 1. We don't need to worry about that for right now. What we want to do right now is get some practice in computing the sample standard deviation. So we're going to need to remind ourselves how we use summation notation, and hopefully that'll come right back to you. So I set things up for us here. Let's keep things simple. Let's just have a very small list of data, and I pick some easy numbers to work with so that we're not wrestling with the math, so that we're understanding the procedures that we're doing. So you can see here, we're going to need to find each component of this equation so we can plug it all in and work it out. So this is asking me to sum something up, right? And I need to ask myself that first question, sum up what? So it's saying take every single score, subtract the mean. Once you find those different scores, square them. Don't sum up anything until you've done that. So in my head, I'm trying to determine what kind of table I'm going to need. I'm going to have to subtract every single score from the mean, so I have a column for that. And that's not going to be enough, though. I don't sum up those values because this is saying sum up squared deviation scores. Here are deviation scores. Here I'm going to square those values. So once I square those values and I have a list of those squared values, then I should have what I'm being asked for right here. So then I can sum up that column. So let's go ahead and work through it. Clearly here I'm going to have to start by computing the mean because I can't subtract the mean from every single score until I know what the mean is. So let's compute the mean real quickly. 6 and 3 is 9. 9 and 9 is 18. 18 and 6 is 24. So a lot of this we can just do in our heads. 24 divided by n, our n equals 1, 2, 3, 4. Okay, so 24 divided by 4 equals 6. So we see that our mean, our sample mean, equals 6. Well, we need to subtract 6 from every single score. 6 minus 6 equals 0. 3 minus 6 equals negative 3. 9 minus 6 equals 3. 6 minus 6 equals 0. All right, well, this actually brings us to a point where we can check our work. If we are subtracting the mean from every single score, these deviation scores should always add up to 0. And you can see in this case they do. I usually focus on the positive numbers and the negative numbers to see if they cancel out. And the only positive numbers that we have here add to 3. The only negative numbers add to negative 3. So they sum up to 0. So I know I'm on the right track. This also helps you understand why we're dealing with squared values. I can't just compute an average deviation score because these deviation scores will always sum up to 0. So how can I compute an average deviation score? Let's first square them. So I'm going to square 0. That equals 0. Negative 3 squared equals 9. 3 squared equals 9. 0 squared equals 0. So now I want to ask myself, do I have a column labeled with what I'm being asked to sum up? I do. So now I can sum up those values. So the sum of the squared deviation scores, in this case, equals 9 and 9, which is 18. We often just denote this as SS, or sum of squares. It's the sum of the squared deviation scores. So at this point, I need to compute something else. And there was my formula, just kind of superimposed on there. At this point now, I need to compute what's known as sample variance. And this is just simply going to take the sum of squares that I just computed divided by n minus 1. And this is just kind of an intermediate step. Because remember, ultimately, I want to compute the square root of all of that. That's what the sample standard deviation is all about. So let's take our sum of squares that we just computed, the sum of the squared deviation scores. It was equal to 18. We're going to divide by n minus 1. 1, 2, 3, 4 is our n. n minus 1 equals 3. 18 divided by 3 equals 6. All right, so that's not exactly what we're interested in, right? Sample variance, as it's known, s squared. Because what that's giving us is an average squared deviation score. What I really want is an average standard deviation score. If I squared all these values in here, how can I get back to standard units? Well, I can take the square root in this next step. So to compute S, sample standard deviation, from S squared, sample variance, let's just take the square root. So in this case, the square root of 6 will equal, and I can't do that in my head, so let's use our calculator. Let's see, 6, and then we'll hit the little square root key, equals 2.449. We'll call that 2.45. Okay, so it equals 2.45. So how are we going to interpret that? I'm sorry, let me go back. We would interpret that by saying that on average, these scores differ from the mean by about 2.45. So you want to write that down. Make sure that you get that in your notes because the interpretation is very important. On average, the scores differ from the mean by 2.45. And we can see that the mean is 6. This differs from 6 by 0. This differs from 6 by 3. This differs by 3. This differs by 0. On average, this is a pretty good estimate of how much those scores all collectively differ from the mean, which we're using as a baseline. So one more time. On average, the scores differ from the mean by 2.45. That's what the standard deviation is telling us. So of course, the smaller the standard deviation is, the less variability there is in our data. The larger the standard deviation is, the more variability we have in our data. Let's go ahead and go through another example. All right, so we want to compute our sum of squares, then our sample variance, and then ultimately the sample standard deviation. So let's first compute our mean, because in order to compute the sum of the squared deviation scores, we have to figure out how much each score deviates from the mean. So let's compute the sum of x. 6 and 8 is 14. 14 and 6 is 20. Okay. We want to divide by our n equals 4. That gives us a mean equal to 5. Let's go ahead and subtract 5 from every single value. 6 minus 5 equals 1. 8 minus 5 equals negative 3. I'm sorry, 8 minus 5 equals positive 3. 0 minus 5 equals negative 5. And 6 minus 5 equals 1. Let's go ahead and check our work. Let's add up the positive values. 1 and 3 is 4, and 1 is 5. Let's add up all the negative values. All we have is a negative 5. 5 and negative 5 cancel out, so I know that that adds up to 0. So I know I'm on the right track, and that also helps me understand why I'm dealing with squared deviation scores, because I can't take a simple average of these deviation scores. They will always sum up to 0. So in order to get an average deviation value, which I want down here for my standard deviation, I first have to go through a little bit more work by first squaring the values. Then I'll take the square root later on to get back down to standard units. If you can tell that story, then you really understand why we're going through this, and you better understand what this measure is all about. So let's square each value. 1 squared is 1, 3 squared is 9, negative 5 squared is 25, 1 squared is 1. All right, do I have a column labeled with what I'm being asked to sum up? Yes, I do, so I can sum them up. 1 and 9 is 10, 10 and 25 is 35, and 1 is 36. So in this case, our sum of the squared deviation scores equals 36. Let's go ahead and compute sample variance, which remember is just kind of an intermediate step before we get to the standard deviation. We can see it's taking the sum of squares, which equals 36, and it's dividing by n minus 1, which in this case would equal 3. So it's essentially computing an average squared deviation score. It's kind of a slightly modified average, but it's essentially an average squared deviation score. And 36 divided by 3 equals 12. Well, we don't want an average squared deviation score. We want an average standard deviation score. So what do I do at this next point? At this next step, I simply take the square root of what I just did. So at this point, we would have the square root of 12. And we can use our calculator real quickly to figure that out. I'm going to type in 12, hit my square root key, and that equals 3.46. Okay, so we've got 3.46 is our standard deviation. And again, how do we interpret that? We're trying to figure out how much these scores differ from the mean on average. So we're finding out that on average, these scores differ from the mean by 3.46. So on average, these scores differ from the mean by about 3.46. So it's a measurement of how much variability there is in the scores using the mean as a baseline. We'll want to practice this, of course. This is a very important measure. Standard deviation is very commonly used, very commonly reported. We want to make sure we can master it. Let's talk about something before we move on. Why are we dividing by n minus 1 when we compute the standard deviation? Why aren't we just taking a basic average? I mean, we're summing up all of these deviation scores. When we compute an average, we sum things up and we divide by the number of scores. Why are we dividing by n minus 1? Let me explain that. Imagine a population of scores, and we usually fall back to like exam scores or intelligence scores. So in the entire population, let's think about intelligence scores. There are going to be some people who have really low intelligence scores, some people who have really high intelligence scores. And of course, most of those intelligence scores are going to group around some type of midpoint, somewhere around 100 for an intelligence test. But we've got variability that starts here and ends here. There's a lot of variability in the population. Now, ultimately, though, we are only going to measure data from a sample because I can't measure the entire population of human beings. And being that as it is, when I select people, even randomly, to be included in my study, because there are so many more people in this range of IQ scores, it's likely that I'm going to include them in my sample. Because there are so few people with these really high scores and so few people with these really low scores, it's just unlikely that they will be selected in my sample, even if I use great sampling procedures. So the bottom line is we know that sample variability tends to be less than the overall population variability from where the sample comes from. So sample variability tends to underestimate the amount of variability in the entire population. So sample variability underestimates that population variability, but if we divide by n-1, we no longer have a biased underestimate of the variability overall. Because think about this for a second. In the formula for computing the standard deviation, we are taking the sum of squares and dividing by n-1. Well, if I divide by n-1, I'm dividing by a smaller number, right? n-1 is a smaller number than n. If I divide by a smaller number, what happens to the answer? It gets bigger. And that might make sense if I show you a couple diagrams of a hypothetical pizza. Let's say I divide that pizza in 4 pieces. Well, each piece is of a particular size. Now let's say I divide that same pizza into n-1 slices. So instead of 4 slices, I divide it into 3 slices. Now each slice is a little bigger. Same thing here. When I divide by n-1, what happens to the sample standard deviation? It gets a little bit bigger. And over the long run, when we use this slightly modified average, when we use this formula, the sample standard deviation will be an unbiased estimator of the population variation. In other words, it will do a good job of representing the variability in that population. And that's exactly what we want it to do. All right, well, that was a lot to take in. Make sure you practice this. That, in general, is the key content from section 4.3, and for now, that is all.